So thanks much for having me. It's so warm outside. You know, frost has already arrived to the northeast, and so this is a welcome little break before I head south to the Southern Ocean in 10 days. So I usually start with my conclusions because I often lose track of time. And so if we don't get any further, I really have two take-home messages. Is we have new ways of doing oceanography that when I was trained, which I'd like to say was not very long ago, but it's getting up there now. How I was trained is not how the graduate students today are going to do science. And that revolution is happening now. And so it's an exciting time for that. And it comes at a critical time based on science needs. So I'm going to give some examples from flying robots into hurricanes, radio tagging penguins and stuff like this, and sort of drive home why we need to do these systems. So if we look at globally what big societal drivers are and why we need to have a very clear picture of what's happening in the ocean, if you look where humans live, they live near coasts, you know, pretty much globally, except for this band here. The majority of humanity is living on the coastlines. The majority of humanity is migrating to the coastline. So if you look at China, essentially the equivalent of the population of Spain is moving from inland China to coastal China every year. So our coastal systems are being impacted. Commerce. Our entire commerce system is based on global transport through the oceans. Coastal fish consumption, if we look at food, the populations, especially in developing nations, are increasingly reliant on seafood for protein. And then there's risks. So if you do tsunami risks, you could do hurricane risks, typhoon risks, you know, but those global issues actually play really well on local issues. So if I look at my home in the Northeast, you know, what do we need to know? We need to know the ocean circulation. I got Arctic water. This is sea surface temperature. So here's cold water from the Arctic. Here's the warm Gulf Stream. And here are rivers pouring in. And I need to understand how that changes the biology. We get tropical storms and hurricanes. You know, here's a picture of the perfect storm that led to the book. Just like Florida, we're one of the big population centers for the United States. Our region's about 25% of the coastal GDP. We have critical habitat. If you want sort of local fish, you get at the fish store, you fish near the coast. If you want the tuna and swordfish and the migratory ones, you're out here at the slope. And the whole system's changing. Our bottom temperatures from the 70s to the present is 5 degrees warmer than it was before. So the global drivers map right onto the local, and we could do the same right here for Fort Pierce, and we would have the same sort of general list. So we need to know the ocean. The problem is the ocean's really complex. And the way nerds say it, the nerds essentially say, well, global circulation maps are dominated by the mesoscale. All that means is there's lots of swirls and squiggles in this, and the energy in these swirls and squiggles drives a lot of the physics of the system as a whole. And that means you have to sample all these squiggles, and that's a very difficult problem because it's difficult to be out in the ocean because this is how we're trained to go to sea. Yeah, so these are the three guys I formed the lab with. I'm the biologist, so that's why I got my head in the water. And it's a joke, but it's not a joke because if you go on a research vessel, a good one, you're not moving much faster than a 10-speed bike. And you're stopping the boat every so often, the ship, and you're dipping your bucket over the side, getting your water sample and making your measurement. And we're trying to describe a biological system that's changing every time the wind changes direction. So obviously there's certain things we can do from ships, and ships will always be a critical tool, but there's many things we miss, and we miss that mesoscale that's so difficult to sample. And while this is a joke, it's not a joke, because here I am in the Antarctic, and I'm hanging over the front of the ship here, trying to get a nice algae sample. And so, you know, if you think of how I was trained to sample, it's really archaic. It hasn't changed in hundreds of years. You know, we only do it in fancier things that cost more money. The other thing about sampling the ocean, it's rough. So here we are on the back deck in the Antarctic. We're linked in, don't worry. But this ship is about 20 feet above the water line, and here we are taking a wave over the side. And what's amazing is we're launching a mooring. So attached on this other end of the line is one of those railroad train wheels, the big steel wheels. And the scary thing is it's going out in that direction. It's not going that direction. And so the great thing is it's a great adventure. The problem is it's a great adventure. There's a lot of times you can't be at sea. And what we're finding out is these extreme events actually are really critically important to understand what's going on in the ocean. So how do we sample extreme conditions? So here's a nice sunny day in the Drake Passage. I'm about 3 stories up on the ship. And, if you want to take a lot of samples, it's not a trivial thing to do. On top of it, on conditions like this, usually your graduate students are in their bunks, cursing you. You can hear them through the walls. And so we're going to need to automate how we essentially sample extreme conditions when we're out there. And so our group essentially focused on that it's our 25th anniversary this year. And so we've been building up technologies that evolved. This is our lab. So this is the cool room. And essentially what it does is we collect lots of data remotely from satellites, shore-based radars, robots, and we feed them into numerical models, just like you see on the weather station, that allow us to do forecasts, to allow us to go back in time, forward in time. And we're doing that 365 days a year, 24/7, because most of it's automated. And we apply that to different areas of study. So if we look at certain things we might study, let's take just a local example from New Jersey. A few years ago, we had this bloom of phytoplankton, this big green blob here. It's the size of the state. The press got hold of it. At first, it was like, oh, there's algae in the water. That's very exciting. Then it quickly transferred into monster algal blooms that led to protests because everyone assumed New York Harbor was dumping all kinds of stuff into the water, and that was creating these monster blooms. It was going to kill everything, and there was a hysteria. In the past, there would have been no way to say, no, it's not coming from New York Harbor, it's coming from here. But the new technologies allow you to do it. So you don't need to look at this much. There's really 3 technologies being shown here. Satellites are the colors. Reds are where you've got lots of algae, so there's your big bloom. Black is where there's clouds. These white lines that are really fine, those are currents. That's what the surface ocean is flowing. And essentially what we've done in the Northeast, and it's being spread around the country now, is set up essentially the speed trap that the policemen use, but we're essentially setting up a speed trap for the ocean with essentially a lot of radar guns all along the coasts that measure the speed of the waves moving towards or away from you. So, and then if we have that data, we can feed into models. You see all these points. And really, when you put all this together, what happened was during that monster bloom, the winds were such that you set up an upwelling, and that led to a big bloom and had nothing to do with New York Harbor. But that's, again, something you could never do before because you never had a holistic picture. Maybe you had a satellite map that told you what was in the water, but you had no idea where the water was going. Radars allowed you to do that. Then to do thought experiments, was it from here or there? That's what the models allow you to do. But all these pictures I'm showing you are surface maps. And so what we need to do is also measure underneath. And so what we've focused on are what we call underwater gliders. We were part of the initial prototypes. This is called a Slocum glider. There's 3 different types. You can whip out your Visa card today, and for $150,000, they'll deliver it. I don't think by Amazon, but it'll show up at your doorstep. And what it is a long-lived robot. There's many propellered robots that are powerful. They have lots of capabilities, but they can't be out there for long periods of time. This robot flies not by propeller, but essentially by changing its weight. It's a buoyancy glider. You essentially balance it very precisely to be close to neutral, and then it sucks in about a bottle's worth of water in its nose. That's just enough to make it heavy, so it starts to sink. There's a big pack of batteries up here, and when you want to sink, you push them forward, so it's just like the old movies on the submarine where you had everyone run to the front of the boat to get the nose down. That's what we're doing with the batteries. And then it sinks. Whoops. And as it sinks, you have wings on it, so it translates into a vertical motion like that. It gets to the depth you want, you push the water out, you pull those batteries back, now the nose is facing up, and so it goes up like this. The big advantage is now you don't have a propeller, which takes a lot of battery power. And so you can go from a day, 2 days, to up to a year. It's slow. It moves about 20 kilometers, 25 kilometers a day. If there's a really strong current, it's going to lose because it's only going at that slow speed, but it can be out there for a very long time, so you don't care. And we've built up a fleet of gliders. We're number 3 behind the U.S. Navy and the National Science Foundation. And these are the deployments just our lab has done. We've done missions across oceans. I'll talk about that. They're mostly education efforts. We've been in Antarctica, we've been up in the Arctic, and all over, a lot in the Gulf too. And so even though we're just a lab, we've been at sea, almost 12,000 days. And while I say $150,000, and it's like, whoa, that's a big deal. That's a third of my mortgage or half of my, well, in Jersey, it's about 10% of my mortgage. But, you got to remember an Antarctic research vessel costs about $75,000 per day just to be down there, even before you start paying for the science. So the robots being out there a year essentially is an order of magnitude less, with orders of magnitude more data. This was actually one of our first tests. It was actually in the Gulf, and it was mapping one of the Carina brevis blooms with a fleet of them off Sarasota. So it's out there for a long period of time. It's pushing water in, sinking, pushing it out, floating. And then every so often it'll inflate a little bag in its back here and gets this antenna above the water line. And that's a global iridium phone that calls the lab. First thing it does is it checks, well, am I off course? The currents push me off. Next thing it checks, is there a human who wants to talk to me? And then usually the humans are asleep. It'll say, okay, well, did the human leave me an email and change my mission and everything like that? So you're interacting with the robot several times a day for a year at a time, a month at a time, depending on the mission. And you're dumping the data back to shore, so even though this guy's at sea, the data is already getting fed in to all the models and everything several times a day. So you can be there continuously, and because they're relatively cheap, we want to move from the concept of telepresence. So before we just had ships, and then with Bob Ballard and seafloor cables, we said we're going to get telepresence in the ocean. Well, now we're in the age of omnipresence, with hundreds to thousands of these systems out in the oceans, all communicating back to shore as it's happening. And that leads to lots of fun experiments. So this is an example of a deployment we did off Australia. We, essentially dropped it in, it flew there. It was in our middle of our nighttime, their daytime, so we all went to sleep. Turns out when we woke up, we realized after we had dropped it off, it had moved much faster than it could into this boat basin and had docked at that dock right there. It had then gotten on Highway 34, gone down Highway 34 and decided to hang out in this house in the front lawn like a lawn troll. We go, whoa, well, that's bad. And so the next thing we said is, let's mess with the guy since we knew he was in this house. We started turning sensors on and off. We had one called an altimeter, which looks for the seafloor, makes a chirping sound. The neighbor in this house looked over the fence and saw this robot in the front, big American flag on it, wings on it, and it was during the first Gulf War. So she actually had the natural reaction, oh my God, it's a cruise missile. Threatened to call the police. The glider got back in a truck, went back in and got dumped in the warehouse districts in a grove of trees there before the guy drove home. And our Australian friends could pick it up, throw it back in the water, and it can go on with its mission. So the idea that we could be anywhere on the planet and adjust a sampling, much less a recovery, is something that would have been inconceivable in about the mid-90s. So this is a revolution we're still realizing to do. We sent the guy a letter pretending to be the CIA, saying don't ever touch our stuff again, and then about a week later we sent him another letter with a bunch of football t-shirts from the university telling him we were just kidding. But now what we can do is essentially combine maps regionally for SST, biology, chlorophyll with ocean color, and now we can fill in these slices with these gliders providing sheets of data. For the first time, we can sample the mesoscale, this biology that dominates the energy of the ocean. So let's take some examples of how we can use this technology to look for things that affect our lives in different ways. So this is Hurricane Irene, and it was predicted to be a very devastating storm to New Jersey. We hadn't had a hurricane in a long time. We had Governor Christie on the beaches there screaming in his usual delicate way, "Get the hell off the beach." He got everyone off the beach. The intensity wasn't actually very strong. It was way over-predicted. And then when Sandy came a year later, people didn't believe him when he screamed on the beach, "Get the hell off the beach," and there was a lot more damage. So what we're going to do is show you the unique physics of this hurricane, because if you look at what the weather centers have done, they've really done an amazing job. Hurricane mortality used to be one of the most destructive events of all the natural events in the US and globally. We've gotten a lot better. We still lose people, but we tend to measure hurricane damage in billions of dollars. While if you look at typhoons in Asia, they still measure the destruction in the thousands dead. So the Weather Service has essentially told us where the storms are going to land. And they do a remarkable job of that, and that's a difficult physics problem that was decades of research. If we look at the intensity forecast of when there's landfall, there's been really no improvement in 30 years, which is a big deal. That affects how you set up all your repair trucks, your rescue trucks, where your personnel are, because that's essentially what drives the storm surge. And we just had all the uncertainty this last time, sort of in the Keys all the way up to Tampa, where there was really no known idea of what the size of that surge was going to be. It was from, oh, it's not going to be bad, to biblical destruction. So we've had no improvement in intensity forecast. That is the unsolved problem. And what we do know is ocean heat modulates the intensity of the storm. So here's Katrina, and here is Katrina coming in, and it passed over some cold water off the tip of Florida, weakened, but happened to hit a warm core ring, and then essentially strengthened right before hitting landfall. So knowing the ocean heat is the critical variable in there. And if you look at the ocean models they use in these forecasts, they actually provide, this is negative down here, 0. So you want to be above 0 to improve the situation. So the models that were being used actually provided negative skill. That's really not a good thing. Generally, if you're going to do this whole thing, you want to have a positive skill impact. And so the ocean models were wrong. So let's look at Irene. This is the sea surface temperature pre-Irene. This is the ocean temperatures post-Irene. Pretty dramatic. It was an 11-degree cooling. And remember, if the ocean's warm, you put energy into a storm. If the ocean's cold, you suck energy out of the storm. We happen to have a glider out there. We didn't actually mean to have it out there for this particular storm, but it was out there. So we're looking at time, depth, the colors represent temperature, and what we have in the mid-Atlantic is a really stratified system. It's one of the strongest thermoclines on Earth, where we go from 25, 26 degrees in the surface down to below 8 degrees within just 6 or 7 feet. So it's a very strong barrier. And what we saw was that before Irene actually hit us, there was a big decrease in the ocean surface temperature. And we could figure out why. The radars showed us that at the beginning of the storm, as it was moving up the coast, was pushing all the water towards the coast. So the water's going in. But it's a 2-layer system, so then it sets up a return flow back out to sea. It wasn't that you got all the hot water down. The key thing was that set up a lot of turbulence and essentially mixed the cold water enough. And you essentially transformed the ocean before the storm arrived, instead of an energy source, into an energy sink. So if you ran the models that were run for the Irene forecast, what do? You need ocean data. What do they use? They use the data they have, satellite data. The problem is once the clouds cover the satellite image, you have no data. So you assume it stays constant. It didn't. So this is what was forecast, and that's what got Christie all hot and bothered. If you actually run it with the real oceans, you essentially predict that size storm, and it represents a difference between a Category 1 hurricane and a tropical storm. It was a 10-knot reduction in peak wind speed, and that was the error in the intensity forecast. So there's an ocean problem. There's lots of complicated atmospheric physics, but it belongs. So let's look at those ocean models. Here's what the glider saw during Hurricane Helene in 2016. Here's that cold bottom water, warm water, and here are the models that are driving our hurricane forecasts. So especially near the coasts where you really need to know the intensity, it's pretty different. So here's what a glider sees, the black line, and there are the two models. Pretty bad, and it's something we're going to need to improve. Here's another representation. Here's the operational GOFS model. So this feeds a lot of not only the operational weather models, but also Navy models. That cold bottom water I talked about doesn't even exist. Everyone wants to improve, so there's now testing of the next model, and we're slowly building the capability in these models to have the right bottom temperature. And until you get the right bottom temperature, you can't figure out what that ocean temp is, and you don't know if it's a source or sink. And so does this process occur? We went through all the storms we could find in the mid-Atlantic, and the ahead of the eye cooling that was sort of not represented in any of the forecast models explained 85 to 94% of the error in those intensity forecasts. All right, does this only happen off New Jersey, that you have this cold bottom water that makes such a unique feature? Well, if you look at the temperature contrast of the ocean between summer and winter in the surface, there's that New Jersey temperature contrast, but you also see it in the typhoon belt of Asia. And they have cold bottom water. That's what that squiggly lines do. And so if we look at the typhoon belts and we look at the storms, we can ask the same question. Can we explain the error? So we looked at Typhoon Mufia, and there's your ahead of the eye cooling that was up to 7 degrees, and explain the errors in the intensity forecast. So the great thing is now we have tools that can be in the ocean. I try to send my graduate students out there all the time. They often object, and so they do not go in the hurricanes. You can't send an undergraduate into a hurricane because the amount of paperwork, if you lose one, is horrific, And so now we have the robots where if worse comes to worse, we lose a robot. And that's sad, but that's something we can just replace. And so we can actually sample areas that we couldn't before. And it has a big impact. So this is Dr. Lou Cellini. You might have seen him during the weather. So he's head of the Weather Service. And he actually came to our data class that sort of works on the big data and challenged the undergraduate students. You better figure out why that US model is not doing as a good job as the European model. You heard it all over the hurricane forecast this year. The Europeans have a better model. I will point out that the US has a better observation network. So that's where we invested. Now we just catch up in our modeling. And the undergraduates for years now have been mining and doing comparisons, and they're actually writing first author Marine Technology Society papers doing it. And so the other thing about these technologies is you can start being a scientist your freshman year. And that's a revolution that, before I was lucky if it started my senior year of really being in the labs. And you can do work that's important. All right, so that's an immediate effect that affects us. Now let's go to an area that's showing big change where it's not going to affect all of us right away in our lifetimes, but is showing big change, and we'll show you how you use technology there. So I work along the West Antarctic Peninsula, and I'm going to tell you the story about the polar Adelie penguin. And if you want more details on it, I'll be speaking at Boca FAU campus tomorrow, and that's where we're really going to geek out on the story. So this is going to be just a quick snapshot. So if you look at the Adelie penguins, there's two polar penguins. There's the Adelies, and those are about like maybe up to my knee. So they're not super tall. And then you got Happy Feet, the emperor penguins, which is about twice the size. Along the coast of, so South America is up here, the Antarctic Peninsula is here, the Adelies breed, that's where their rookeries are, and their rookeries aren't spread out evenly along the peninsula, they're in specific locations. So there's a big breeding colony at Anvers Island, Renault, Adelie, and we know this because we've been doing surveys for decades, and we've been putting radio tags on the penguin. Look at this guy, he's all tricked out. Ladies love him, yeah. And so up in the north, we've had people essentially doing censuses since the 70s, and what have we seen in the Adelie penguins? Their populations have collapsed. The prediction right now is we don't know if it's going to be 5 or 10 years before they're gone from Anvers Island. Doesn't mean that biology disappears. New species of penguin are moving in from essentially South America. Chin straps and gentoos, and so you can see them surging in, but at much lower numbers. So the questions we had is, why do they form colonies in specific locations? And what's happening with this decline? Well, the thing that's happening in the West Antarctic Peninsula, it's warming. So this is 1940, 2010 on this plot. This is a winter average air temperature. So there's warmer winters, colder winters, but if you look at the long term, it's been getting warmer. And so it's raising just about 1 degree C in the winter per decade. That doesn't sound like much, but think of it, you're near the ocean, so you pretty much hover around freezing along the maritime places of the Southern Ocean, southern continent. And what we see is if you're right around freezing, think of it like your freezer. You go out, you buy your Ben & Jerry's ice cream, it's at -2, it's perfect, and then some jerk walks in your house and dials it up to 3 degrees, and your ice cream goes from perfect to not so perfect. And we're seeing that process happen over 50, 60 years with actual data. So Palmer Station is a U.S. Antarctic base. It's located right on this tip of land. It's surrounded by the Mar Glacier. And what we're looking at is the location of the Mar glaciers from the 70s to 2013. And we can see it's retreating football fields over decades. The glacier is melting. In fact, it's melting so much so that under this glacier, we're discovering new islands that we didn't know existed. So we're getting to name islands. So Chuck Amsler is an old friend, and now there's Amsler Island, and there's a Doug Martinson Island. So the fact is it's crazy that we can go to a place where we still don't even know if there's islands. And so that winter is warming, you're not forming as much ice, and you're seeing a big glacial retreat. It's retreating enough where you're starting to form soil. So these are when you go on some of the islands, and so what we're seeing is the greening of Antarctica. And really the standing bet among people working down there is, in what decade will we have rooted plants? It'll probably happen in my lifetime, you know. And beyond the societal things and everything like that, as a nerd, what a great experiment. You know, my career is about 30, 40 years, and the whole thing's going to flip in 30, 40 years. So we can track this. The old way was, again, based on using old technologies where we were really limited. So this is how we used to call home. It's a ham operator room. This was the room I found out where I was going to graduate school. It was one-way communication. I don't know for those of you who are familiar with ham radios. So you have your conversation. Hi, dear, I love you, and then over, and everyone flips a switch. And she gets on the phone. The whole world is listening to the conversation. I hate you. Where are you? Over. It's very affirming. And you compare that now with this omnipresence idea. So the red line is a glider that was launched from our ship. It did a survey near some penguin colonies, flew in, and got picked up by the British remotely. This guy here was the one who directed the British in, and we were out serving somewhere else. He had a date in New York City, so he wanted to move up the recovery time, and he was able to change the protocols for the glider to get it there quickly and call the British while driving in his car to a date in New York City. So again, this concept of omnipresence and sampling extreme parts of the planet is now doable. So what's melting the West Antarctic? The atmosphere is getting warmer. There's only one heat source that has enough energy to explain that warming, and it's the deep ocean. So the continent is surrounded by the Antarctic Circumpolar Current. It's the largest contiguous current on the planet. It runs at about the force of about 30 Niagara Falls continuously around the continent. It is a balmy, 4 degrees, balmy by Florida standards. And there's two areas where the continent is melting fast. It's melting here along the peninsula, and it's melting over here by the Totten Ice Shelf. And the reason they're melting here is this is where the current goes closest to the land. The Ross Sea, you'll read reports, is still growing ice, and essentially the ACC is pushed way offshore in that location. So the heat in the atmosphere is coming from the deep ocean, and the deep ocean here is about 300 meters deep. So the deep ocean essentially circulates up, and then it breaks like waves up onto the continental shelf and diffuses heat into the upper ocean, into the atmosphere. So what's melting Antarctica and warming the atmosphere is the deep ocean. And we know the deep ocean has enough heat and has warmed enough in recent years that even if you shut down carbon emissions today, this melting will continue for about 150 years, just based on the heat content in the deep ocean. That's an estimate. The West Antarctic ice sheet is as big as the Greenland ice sheet, and it's in unavoidable melting collapse. What's happening is this warm current is now getting underneath it, and you're melting it from below, and then it's sliding into the ocean. We don't know if it's going to take 100 years, 1,000 years till you have the full retreat of the West Antarctic ice sheet, but that represents about 3 feet of sea level rise. And we are used to thinking in terms of inches and everything like this. The Totten ice sheet, that's where you're talking about over 30 feet, if that ever melts. Yeah. So when that wave that's running along the coast here breaks, it's essentially undersea eddies that are spilling. So these are blobs of warm water that the gliders have sampled. That's the trajectory. And so you can see these eddies. And so because we have these robots, we're able to essentially patrol and find these undersea features you can't see from a satellite and essentially count them and measure how much heat they're carrying across the coastline and heating the whole system. And if you think about a technology, it's a really cool problem. How do I surf a wave or an eddy that's through, we think it in terms of feet, almost 1,000 feet under the surface of the ocean remotely from New Jersey? And the fact is we can. So one of these eddies here, we were able to follow for 7 days and could essentially follow the heat diffusion. So the heat gets transported on the coast, and it happens to go in very, very specific locations. And they're guided, essentially terminating where the penguin colonies are. So the penguin colonies are always next to these deep sea canyons that were glacially scarred. And when this was completely ice covered, the penguins still needed access to the ocean in the wintertime. The only time in the winter that had open water were these glacially carved canyons where the warm water from the deep sea would upwell up and potentially form what we call polynyas, areas of open water. So that can explain why the penguins are where they are. But we never had any evidence. But now with gliders, we could essentially fly in. And so here we are flying around Palmer Station. There's a penguin colony there. There's your upwelling of warm water. Here we're down at another island, Avian Island colonies on this side. The purple there is where they forage, and you can see the warm water there. Down in Charcot, essentially, you can see the blip there. So now we know where to look, where are the on-ramps for this hot water that's melting the system. And that's something we could have never sampled using shipboard approaches. Now we want to know, why is it a hot spot? Why are they foraging in those locations? So we have lots of these radio-tagged penguins. We have sort of historical climatologies of where the different ones do. So now we just keep the gliders out there flying all the time to essentially sample the physics. What is it, the physics where you're essentially coagulating material in a certain location? Or is there a lot of biological activity promoted in that region? It's growing. We do that to look at seasonal things, but then if we want to do real-time stuff, we essentially have the penguins out. They send data back as they're swimming around. We use the real-time data to program in propeller gliders that are much faster to go in and sample the hardcore physics. So you combine many different tools, including animals, because evolution's really smart. They know how to hunt this area to essentially figure out the physics and the biological productivity. So it's sort of the animals informing the robots, and then the humans essentially modifying the missions to figure out the heating. Turns out that the main thing the Adeli's doing is it's very conservative. It's a polar species. It was evolved to essentially have 2 months to put enough fat on the chicks every summer to survive the next winter. It's something like 4-point-some kilograms it has to put of fat on a chick for it to survive. And so they always found that there was highly productive food here, and they always go there. Well, the water's warmed, and the fish have changed. And the fish they were hunting here are no longer there. The fish are over here. But the Adélie penguins are very conservative, so they're continuing to go out what's done their families well for decades. And it's the South American penguins who have more malleable in their behavior that have adjusted. That'll completely flip if it gets cold again. I'm not saying that these guys are doomed, but they are essentially adapted to a polar species. All right, so we got all these cool toys, we got all these cool locations, we got real-time data. The other thing we need is more people looking at the data. So that's why we're essentially trying to turn the ocean into our classroom. Because here's a traditional thing. Here's a great lecture where I really roused the students in Taiwan. It was a great lecture on sediment transport. And then sort of lectures like that lead to these kind of behaviors. This is Whisper, which is sort of high school questions about life. And the quote here, I don't want to be a math and science teacher. No one wants to marry a boring person like that. I don't want to die alone. And so I would argue that we better do a better job of actually showing how fun and creative science is, because it is actually an amazing adventure every day I walk into the lab. And robots are a great tool to that. If you do a Google search for a robot, look at all the different categories. And, if I actually ask, why did I become a scientist? Well, my dad was a scientist, and so we would build things in the back house. And he'd make me watch Star Trek and Jacques Cousteau, and those things pretty much changed my life. We had a glider that flew across the ocean. I'll talk about that in a sec. Here it is. And here it is, 185 friends after only 3 weeks. I think I crossed 200 last year after 10 years. Highly depressing. But it's a great magnet, and we should use it. So a few of us were at a conference in Lithuania, and Dr. Rick Spinrad, who was an assistant administrator for NOAA at the time, says, I want to take you guys out for a drink. So I was like, great, this is going to be fun. We're going to talk. And this is how the conversation started. First sentence, I have something you need to do for the good of your country. Whoa. And so we ordered another drink. But then essentially what he said was he thinks scientists, especially in times when funding is tight, they get risk adverse. They stop taking risks because they don't want to lose their equipment. They're worried about their future. And actually you have to do the opposite. You have to take the big risks because that's where the big payoff was. And so his challenge was, I want you to have students, undergraduates, fly a robot across an ocean. And I want you to get them to be excited about doing scientists to address the gathering storm, which was a National Academy report that pointed out the U.S. thrived after World War II. What did we have? We had the best scientists and engineers. We had cheap energy. And we essentially cornered the market in lots of industries and did very well. Energy markets are in flux. And you can actually argue that the U.S. is lagging now behind our Asian and European counterpartners. So he was challenging us to do that. Our longest mission at that time in 2006 was that green line. And he was proposing this. And again, the power budget for a mission like this is about 3 of those little Christmas tree lights per day of energy. So you had to redesign the robot to be much more efficient. And you also had to redesign a long mission where you had no roadmap because the ocean models weren't believable. The first time they tried, the students, this is the class, it started with a cohort of 3 or 4 students, and then every year continued to increase. Right now, we are pretty much at a steady state of 75 and 75 students every year. The first one they launched, it got all the way to the Azores. It was eaten by a shark. We know it was eaten by a shark because it was struck from below at about 70 meters in the middle of nowhere. It got to the surface, it panicked, it blew its weight, came up, screamed for help. Our first reaction was download the engineering data. You could see the point of impact. It was right by the middle, by the CTD. That's what started leaking. So we knew what to repair. And we essentially watched it drift away into the deep sea. We came back. All the students were crying. They were devastated. And the point was no, you're supposed to fail in science. A good experiment often tells you something, and now we got to redo it again. Second one, got all the way across the Atlantic Ocean. It made it to Bayona, Spain. That's the town they picked out. That was the town that Columbus's ship, the Pinta, returned with the first news of the New World. And so Bayona hosted a big party with all the school kids and everything like that, and they actually flew over a whole cohort of undergraduates. So these are undergraduates being pioneers and explorers well before they're graduated. It makes them excited, but more importantly, they got to learn quantitative skills that they can take to the energy sector, they can take to the federal sector, they can take to the state sector. And it's turned into this class where now it's expanded. So we're doing longer term missions. We just finished a South Atlantic bight. We just landed a leg from Australia to Sri Lanka. Now we have companies coming in and getting our student teams to essentially work on calibrating new sensors and everything like that, as well as doing the Lou Ussolini term, and they've got to present their materials and do it. And the great thing that makes me most proud about this class is about 30% of the kids are non-science majors. They're political science, they're religious studies, they're language studies. They're actually going to go get jobs that are important, business majors, right, where they're movers of society. We need them to be ocean literate. It's one thing to be science literate, but for those of us that live in coastal states, we know that our population needs to be more ocean literate. And so it's a way to entrain them. So now I'm just going to end with, where are we going with all these technologies? Well, we need sensors. Platforms, the age of building sexy platforms, that's sort of at a sunset phase. We have great platforms. Now we need to measure things. So if you look at a food web, you want to measure all these boxes, and there's all these things you want to measure. The greens are where we have sensors that a glider can carry now. That's just for this particular robot. Oranges are where we're about 6 months away. Reds are where we have lots of work to do. So we need sensors. We need our robots to be smarter because sometimes we sleep and also sometimes humans are not smart. So here we're working on building a smarter glider by essentially porting in essentially a supercomputer chip. The only reason that's possible now is because there's been development to develop low-power supercomputer chips. So here we've told the glider its depth, and then here's temperature on this axis, to essentially find where's the thermocline and analyze its own data and then hover at the thermocline. So the glider does EO, up, thermocline's here, and there it is hovering, looking at its own data and thinking. That's going to allow us to see things when a human can't communicate to it, because when it's underwater, we can't talk to it. It's not till it comes to the surface. We need biofouling improvements. You know, it's an ancient sailor problem, and it still affects us now. So here is a glider that maybe spent a little bit time. I figure this is my Yuletide Christmas card this year. Look at that Santa beard. Yeah. And so what are the materials and also the behaviors of the glider and other robots to minimize the fouling by being smart of where they fly in the ocean? You know, so there's whole areas of growth there. But the main thing is we got to be scalable. Because if I know with my technicians, I got a glider technician, Dave, we call him the glider whisperer. If I have him running more than 7 glider missions at a given time, that's about when he snaps. If I get him up to about 10, that's when he just explodes, like a drummer from Spinal Tap. And so how do you build a scalable system? Well, you got to take as much of the human out of the loop as you can. And so the way to do that is to automate decision making based on what the future ocean is going to be that the gliders are going to be in, not the ocean that you saw when you dropped it off. How do we do that? Well, just like a weather model, we can run ocean models that give us a forecast. In the future forecast model, we can put in essentially representations of gliders, so we can see how a glider is going to fly in a future ocean. We have gliders in the water, and essentially it collects data that goes back into the model, and so it's a loop. The model is essentially telling the glider where to fly based on the mission, and then the glider's getting more data that's improving the next forecast. And the scientist sits in the middle here of setting what are the science priorities. I want to look at a river plume. I want to look at a harmful algal bloom. I want to look at this. But I don't want to have to decide every 6 hours the waypoints, because that's essentially where it becomes too much if you have a fleet of 30, 40 gliders out there. So we did that, and so we essentially, after much conversation, essentially allowed our gliders, 4 of them we put in the water, to be handed over to be controlled by a mathematical ocean model. And again, you know, each one's $150,000, so there's $600,000 you're essentially handing over to a math game. And we have it in a Google thing, so this yellow halo is where a glider can reach as you go in the future. I think this halo represents, in 24 hours, this glider can reach anywhere in this yellow halo. And so you can decide what the science mission is. And so we handed over control for about a week of the gliders, and then we asked the question, how good did it do? So this is the position different from the plan. And this black line right here is the resolution of the model. So you can't ask the model to do better than below this line. And it's these points here that says there was a really bad location difference. And so my first reaction was the models suck. I'm an observationalist. But actually, if you look at it, this was a compass failure on the glider. This was a delayed call-in, so the data didn't go into the thing. So actually, the automated ocean models were good enough so they could actually fly the gliders without a human in the loop. It was a machine controlling a machine. Terminator? Wait till they become self-aware. We want to take it one step further. All right, there are some satellites, like the NASA Hyperion satellite, that's tiltable. And so you can change where it's looking. And we're saying, okay, if we have math models controlling these robots, can these robots then control this satellite? And so we plugged it in, so essentially it goes right into the science event planning in NASA, and it's a whole series of software steps. And we essentially wanted to hand over the control of the Hyperion satellite to that glider there. So here's the swath for that particular mission. It was handed over to this one. There's the waypoint. This swath of the satellite was supposed to fly over this part of land, but it was essentially redirected by a robot controlled by another machine. So it's a multi-layered machine controlling a network. And that is a scalable system that allow us to outfit the ocean in ways we never thought possible. So it's sort of a lot of vignettes, but really take-home messages. We have new technologies, and the most important thing now isn't getting new technologies per se, but it's learning how to be really creative in using them, because this is a whole different way to do research than you're traditionally trained. I wish I was an undergraduate now. The stuff they're going to do is so cool. And as we get insights, we're going to discover real fundamental processes, like what controls hurricane intensity at landfall, something that affects us all, because we have the data. And that if we do this right, we're actually going to enable the U.S. to sort of regain leadership and train the next generation of great scientists and great engineers that are going to lead to prosperity and great solutions. So I think it's an exciting and great time, and I thank you for your attention.